All right, so in at least for our third test, let's just remind ourselves some of the stuff that we were talking about, at least where we were going. What we did right before we got to this particular set of material is we had some type of a population, right, where it had some type of a mean and a standard deviation. And what we would do is we would kind of pull out one person at a time, right, and we try to find the probability that we got a score bigger than that or less than that, right? So what we did was we kind of drew our normal curve, put our mean on there, marked where we got our number from the sample, and then found the probability of being bigger than or less than that, depending on the question that we were asking. Right? And then what we started to move to was the idea of what happens if I pull out a sample, right, from maybe the same population with a mean and a standard deviation. Right? What do I know about the sample? Well, in order to answer questions about the sample, we had to know the sampling distribution, right? Where if this was already normal, then every sample was already normal, right? But if this was not normal or non-normal, then we had some checks we had to do, right? Depending if we're looking at proportions or averages, we looked at either what p, I'm sorry, what was that? P times 1 minus p times n, making sure that that's bigger than or equal to 10. Or if we were looking at averages, as long as that sample size was bigger than or equal to 30. So we had a few checks we had to do depending on what setting that we were in. Right? And then if we could use it, remember the samples all had a normal distribution where the average of the sample was the same thing as the average of the population, and the standard deviation of the sample was the standard deviation of the population over the square root of n. Okay? So keeping that in mind, let's look at problem 1 on our third test. All right, because in problem 1, we look at two different cases. The first case deals with what happens if we pull things out one at a time, and then the second case is what happens if we pull out, in this case, 16 at a time to make our sample. Okay. All right, so here's number 1. All right. What we have is a population of cars, right, to where the average miles per gallon is 32, and the standard deviation of miles per gallon is 3.5, right? So again, those are for individual cars, individual Chevy Cobalts. Right? So for part A, we're taking a sample of size 1, right? Which means our distribution is normal, right? Let's see, because we're told that in the problem that this distribution was normally distributed. And for a single score, single car, the average is 32, standard deviation is 3.5, right? So that's what part A is. When we say, what's the distribution for single cars? That's what it is. Right? So for part B, the question was, what's the probability I will pull out a sample average of just one car getting 31 miles per gallon or less? Right? So again, here is our picture. 32. So we want to find the probability of getting 31 or less. So what we do is we use this distribution to get my z-score. Right? So here the z-score is just 31 minus the average over the standard deviation. Okay, and in this case, that gave me negative 0.29. Right? And if you look this up in your charts, that negative 0.29, remember, it gives me the area from here on back, which is what we're looking for. That's 0.3859. Okay? So the probability of this happening is 0.3859. The percentage chance it happens would be 38.59%. Okay? All right, and then for part C, what we started doing is we started pulling out samples of size 16. Right? So for part C says, all right, what's the distribution look like for all those samples of size 16? Right? So what we do is we know that it's going to be a normal distribution since it already started off as normal. Right? The average of the samples is going to be the same thing as the average of that population. Right? And then the new standard deviation is just the old standard deviation over the square root of my sample size. Right? So that means it'll be normal, average of 32, square root of 16 is just 4, which means this is a normal distribution, an average of 32, and that divides out to be 0.875. Right? So that's what the distribution is for samples of size 16. And then part D asks us this particular question. What's my probability that the sample of size 16 will have an average of less than 31? So again, here's my picture. There's 32, there's 31. So we're trying to find this probability for now samples of size 16. Okay. So to get this z-score, it'll take the 31 minus the average, and then divide this by the standard deviation, which in this case is 0.875. Right? And then that gives me a z-score for these samples of size 16 of negative 1.14. Right? And then if we look that number up in our charts, we get 0.1271. Right? So it has a little bit less than a 13% chance of actually happening. Okay. All right, so when we're looking at these types of problems, we have to ask ourselves that question of what distribution are we using, because that will set up for me, is it normal, is it uniform, what the mean is, what the standard deviation is. So we have to kind of get that straightened out before we actually start to answer the questions. Okay. All right, so for number one, we just looked at the population one term at a time and then 16 at a time. Right? So any questions with how we came up with those particular numbers on this first test and what we were talking about on it, at least all those ideas for our sampling distribution? All right. All right, well then moving on, if we look at some of the other ideas we had throughout our third test, right? Problem number two kind of looks like this thing, to where we have a sample, a population of women ages 40 to 44, right? And these women have never given birth. All right, let's see. So what we're going to do is we're going to pull out a sample of size 144. Right? So we'll talk to 144 of these women, right? And of these women, at least of the women in the sample, 30 said that they have never given birth. Okay. Let's see. All right, so the Pew Research study said that all of these women, at least a proportion of these women, should be 0.18. Okay. In our sample, we found 30 out of the 144 had never given birth. So the sample proportion, which we denote with a p hat, is 30 out of 144. Right? And if you multiply that out, you get 0.208. Okay? So now the question asks us this: what is the probability that this sample would occur if they are correct? Right? So in this case, we're taking a sample of size 144. Right? So since we're taking a pretty big sample, we should be okay, but we can still check it. Right? If I'd looked at n times p times 1 minus p, that gives me 144 times 0.18 times 0.82. Right? And let me see what this number is. 144 times 0.8 times 0.82. Yeah, it's like 21.25-ish, something like that. Okay. All right. So we can definitely use these types of settings. So let's see. Okay. So what we need to do is figure out what is the sampling distribution for samples of size 144. Right? Well, based on our work already, we know it should be about normal. Okay. The average of the samples, right, if they are correct, should be 0.18. And then how do we find the standard deviation for these samples? Because it wasn't given to us in the problem. So the way we estimate it if we're not given the number in the problem is by computing this sigma of p hat, which is the square root of p hat times 1 minus p hat over the sample size. Right. So that's just a square root of 0.208 times 0.792 all over 144, which gives me a standard deviation of 0.034. So this is what we're going to be using to answer questions about samples of size 144. Right. And the question that we're given is, what's my probability that this sample would occur, right? Assuming that this probability is correct. Right? So, in other words, if we have 0.18 here, what's my probability of getting 0.208 or higher? Right? So for this z-score, again, take our observation, subtract that mean, divide by the standard deviation, right? And I get a z-score of 0.82. Right? And then if we look that number up in our charts, right, the area from here on back is 0.7939, which means this area, if we subtract it from 1, is 0.2061. Right? So the probability is 0.2061. The percentage chance is 20.61. Right? But again, this was an exercise of understanding what the distribution is that we had to use in order to answer the question. Because if we never even get to here, then there's no way we can accurately answer the question. All right, so any questions on that sampling distribution for the proportions? You all doing all right with that so far? Okay. All right, well, if we keep on going, there was another example of these where we did a tad more work as well. Right? So on number 3 here, we have again our population, right? And the question is about healthcare. Right? And in this particular problem, we have no clue what the mean or standard deviation is for the population. Right? But we're going to try to figure out at least a bound for it using some confidence intervals. Okay? So what we'll do to try to catch that is I will take a sample of size 1050. Right? And the question is, should the government be responsible for health care? Okay? So in our sample of size 150, we had 493 people say yes, that the government should be responsible for health care. Okay? So for part A, it asks us for an estimate on this number, the mean, which I guess in this case, since it's a proportion, it really should be a p and not a mu. Right? So we're going to try to estimate p. And the way we do that is we're going to use p hat, right? Where that's the number that comes from the sample. So that's 493 out of 1050. Right? And if you divide that out, you get 0.47, and it rounds up to 0. Okay? All right, so if we had to guess what the proportion was for the entire population, we would guess this number. Right? I mean, we honestly don't know, but that's our guess based on the sample. Right? So that's part A. That's our point estimate. Right? So we're going to try to make a confidence interval to see if we can actually capture this number P, right? At least a 90% confidence interval. So we need to do our check to make sure we can do all these things accurately. Right? So for part B, we are using a simple random sample. That's how we got those 1,050 people. If you look at n times p times 1 minus p, which in this case is 1,050 times 0.47 times 0.53, we get 261.5 or 0.6. Right? Definitely bigger than 10, so that check works out. Right? And then, is this an independent sample? Right? The way we're checking it is we're wondering if the size of the sample is less than or equal to 0.05 times the size of the population. Right? Well, again, if we talk about all adult Americans here, we're talking these are millions of people. Right? So yeah, so if I take 1,050 and multiply it by 20, I get 20,000 or so. So that's definitely less than this number. So we can assume it's independent too. All right. So now what we're going to do next is try to set up a confidence interval to try to capture this number P, right? And we're going to try to make a 90% confidence interval, right? Which, if you remember, if we're using proportions for our confidence scores, our z-scores or t-scores, we use z-scores for proportions. And for a 90% confidence interval, that's a z-score of 1.645. Right? If we were trying to find mu, we'd use t-scores, right? But since we're trying to find p, we're using z-scores. Right? So we need to come up with this formula then. Right? It's p hat. We're going to start at that point estimate, And then we're going to add that margin of error, which is just that z-score times my standard deviation. Right? And the standard deviation for these samples, right, if we use that same formula, gives me 0.47 times 0.53 over 1050, which gives me a simplification of 0.015. Right. All right, so in this case, p hat is 0.47, my z-score is 1.645, my standard deviation is 0.015, so that's 0.7 plus or minus 0.025, and if we add it, I get 0.495, and if I subtract it, I get 0.445. Right? So there's my 90% confidence interval. And if you remember what that means, that doesn't mean I'm 90% sure it's in there. What it means is 90% of the time, these techniques will actually capture that true value for P. Right? That's all this confidence interval means. All right, so any questions of how we calculated any of those numbers for our confidence interval? You all doing okay so far? Okay. All right, the next problem in our test just kind of talked about t-scores and just looking them up, so I'll let you all mess around with that. Let's just get to the applications here. Let's see, on number 5, we are talking to, again, our population here is American adults. Right? And the claim is that 80% eat salads. Okay? Now, if you read through the question here, this looks like it's a proportion, right? So they're claiming that P equals 0.8. Okay? So a nutritionist is curious about this number, so she polls a sample of size 150, right? And she finds that X, the number that eats salad, is 130, right? So we want to make a hypothesis test at the alpha equals 0.05 level just to test if their claim that P equals 0.8 is correct or not. Okay. All right. So for this one, the claim is that P is 0.8. Right. The nutritionist thinks that it should be different. Right. So the null hypothesis would be that P is not 0.8. Right. So to calculate the test statistic, or our sample proportion, we need to calculate P hat, which is 130 out of 150 people actually ate salad, right, at least during that time. So if we divide that out, I get 0.87. Okay, so that's my value for P hat. Okay. In order to answer these particular questions, we're going to need our standard deviation. So what's my standard deviation going to be here? Now remember, for this one, we're assuming that their claim is correct. Right? So what I'm going to do when I calculate this formula is I'm not going to use 0.87. I'm assuming they are right. So I'm going to use 0.8 as my value for P, which means 1 minus P is 0.2, and I'll divide that by my sample size. Right? And if you multiply all that stuff out, you get 0.033. Okay. All right. So now to get our test statistic, our z-score, it's just the number from our sample, that proportion, minus the claim over the standard deviation, and I get a z-score of 0.212. Okay. All right. So here, let's see, I have a z-score of 0.212, and again, if you look that one up in our charts and go back, we get a probability of 0.9830. Which means if I subtract that from 1, I get 0.0160. Right? So my p-value is 0.0160. I'm testing that at the alpha level of 0.05. So in this case, p is actually less than alpha. Right? Whenever your p-score, your probability is less than your threshold there, that tells us to reject the null hypothesis. Right? All right, so in this case, we believe it actually is. Let me read through this real quick. I might have set something up a little bit. Oh, no, you know what? I said one thing and did another. Right. I read one way but wrote down another way, right? They want to find the probability if it's higher than this number. So this really should be P is bigger than 0.8. Yeah, so my bad. I just kind of messed that up and read that wrong. Okay. Because I started thinking, since it was a two-tailed test, we should have had to calculate this probability down here. But when I went back and reread the problem, it actually said higher, not different. Okay, so we really just need to find that part. All right, so there is that one. Now let's look at a hypothesis test where we have to use a t-score. All right, so here we're again looking at American households. Right, so there's my population, our households. And the claim is that the mean, right, it actually uses the word mean in there, which tells me that this is mu. The mean expenditure for energy is $17.50. Okay, so an economist wants to know whether this has changed, right? So in this case, the null hypothesis is that mean is $17.50. The economist wants to see if it's changed, which means the mean is just not $17.50. Right? So the economist pulled out a sample of size 25, which is a little problematic because it's kind of small, but let's see. One of the questions we're asking in part A is, what do we have to assume in order to do this? Right. Well, we're actually not told anything about this population other than the average is 1750. Okay? So we don't know if it's normal or if it's not normal. So in order to go through this process, we either have to take really big samples, right, 30 or more, which we're not doing that, or it has to be at least a normal distribution. Okay? So since we're going to go ahead and carry out this test, we have to assume that our population is actually normal. Okay? So the assumption that we're making here is that the population is normal. Right? And we're doing that because our sample size is less than 30. Right? So we can't just assume that the sample is big enough to make it a normal sampling distribution. Okay? So this is an assumption that we're kind of making in the background just to get this problem done. So that's what part A was on the test. Okay? All right. So then we were asked to carry out the test for this. So we've already stated our null and alternative hypothesis. We need to come up with our standard deviations for these samples of size 25. Okay? So in this case, the standard deviation of the samples, which we'll say sigma x bar represents the samples, is the standard deviation of the population over the square root of n. Okay? And if you read through the problem, we're actually given a little bit of help here, where we're told the mean is 1750 and the standard deviation is 364. Okay? So the standard deviation for the samples is the populations over the square root of my sample size. Right? Which means in this case, I'm just dividing it through by 5, so I get 72.8. Okay? So for samples of size 25, right, we were assuming they were normal. Right? The average of the sample should be the average of the population, and the standard deviation of the sample is not this number, right? Because this is a number for one term at a time. The standard deviation for samples of size 25 is that one, 72.8. Okay? So that's what we're working with. Okay? All right. Now also, since we are using averages here and not proportions, our test statistic is a t-score. Right? Those go with means or averages. Right? Now to get the t-score, it's the same idea as a z-score. You take your number from the sample, subtract the number given from the population, and then you divide by the standard deviation of the samples. So in this case, the number from the sample was, let's see, did I actually write that down yet? Let me go back and read it. Yeah, so the average from the sample was 1923. All right, so this will be 1923 minus the claim, which is 1750, over the standard deviation of the sample, which is 72.8. Right? And then if you multiply all this stuff out, you get 2.376. Right? So now, since this is a t-statistic, we need to use our t-charts. And remember, we use what's called degrees of freedom on these charts, which is just my sample size minus 1. So in this case, it's 24. Right? So what we'll do is let's go to our charts. Right? So let me put that chart in here. Right here. We go to a sample of size 24, which is right there. And remember, the t-score is 2.376. And if we blow this up, 2.376 occurs between here and here, right? Which represents these p-values. So that says the p-value is between 0.01 and 0.02. Right? So if we go back over here, remember our t-distribution is a little bit fatter than the normal distribution. Right? The average was 1750. We want to find the probability of getting a t-score of 2.376 or worse or higher. And since it's a two-tailed test, we would use negative 2.376 and lower. Right? And for this part right here, I just found that that p-value floats between 0.1 and 0.2, which means by symmetry, this is between 0.01 and 0.02. So if we add those two together, you get 0.02 and 0.04. Right? So there's my p-value for this particular test. Right? And what we're asked to do for this two-tailed test is compare this at the alpha level of 0.05. Okay? So here again, p is less than alpha. So that tells me to reject the null hypothesis. Okay. All right. So that's how we could do one of these hypothesis tests using a t-score. Right? So remember, t-scores go with averages or means. Z-scores go with proportions. Okay. Now for a two-tailed test, remember we could do this a different way by creating a confidence interval and see if their claim falls inside that confidence interval. Right? So let's run through that real quick. So here, the claim is that mu was 1750. Right? And we're going to make our confidence interval the same way we kind of did the others. Right? What we'll do is we'll take x bar. In this case, instead of a z-score, we're using our t-score. Right? And then it's the standard deviation over the square root of n again. Right? But we already found that number to be 72.8. Okay? All right, and here we are making a test score, or at least a confidence interval based on alpha being 0.05, which means we want to have 5% total in these two tails, which means this gets half of it and this gets half of it. Okay. So we know x bar from the problem, from the sample, was 1923. We know our standard deviation was 72.8, so we need to figure out what this t-score is. Right? So remember, our degrees of freedom are 24. So what we'll do is we'll look at our charts and see if we can figure out where this probability comes into play. All right. So let's go back here and let me erase this. All right. So we have, again, 24 degrees of freedom. We want 0.025, which is this column right here. So if we kind of blow this up, and can I make this where you can see it? Looks like it's that number right there, which is 2.064. So 2.064 is the t-score that we have to use here. Right. So if you multiply those two numbers together, right, we get 150.3. And if we add 150.3, we get 2073.3. And if I subtract it from 1923, I get 177.2.7. Okay? And remember, their claim is that mu is 1750. where if you look at our confidence interval, mu is not in the confidence interval. All right, which tells me to reject H naught, right, which we knew we were going to do anyway. Okay. All right, so again, remember the confidence interval, that's only valid for a two-tailed test. So make sure you only try to use those at that point. Okay. All right, so that was kind of it for test 3, right? We talked about some normal distribution stuff, looked at normal distributions for different size samples, then moved on to proportions, moved on to means, did some confidence intervals, did some hypothesis testing, and those were kind of the ideas that we were using for test 3. Okay. All right, any questions about these particular problems that we were going over? Any of the ideas you want to talk about again or do some extra problems on?